Hi, welcome to AP Physics C, Unit 12. This is the unit on magnetic fields and electromagnetism. So let's first dive into what are magnetic fields. So when it comes down to the end, this is more of a conceptual concept or topic. You're going to see one equation, but mostly this is really laying the groundwork for those magnetic fields that we'll talk about. So first of all, a magnetic field is going to be a vector field, much like E fields. That can be used to determine magnetic force exerted on moving charges, currents, and magnetic materials, right? So one thing to note is that there are never monopoles. And what that means is that all magnetic materials will have a north and a south end. And so you can also represent magnetic fields as vector field maps, just like we did with E fields. The field lines are going to form closed loops. So this is where E fields and magnetic fields differ, because in electric fields, they were open-ended, right? They just went from one, positive to negative. They didn't form loops. But what happens is with magnetic fields, they're going to form loops, right? And this is based on and described by Gauss's law of magnetism, which is going to be our second equation in Maxwell's laws. The first one was Gauss's law of electricity. And so Gauss's law of magnetism says that the integral over a closed loop of the magnetic field strength dot the area vector, right, or dA, is going to be equal to 0. So that is the second law. And a lot of what we're going to do in terms of calculating is going to be centered around this B dot dA for magnetic fields. So magnetic dipoles will result from the circular or rotational motion of electric charges. And so what happens is if you were to break a magnet, especially a bar magnet, all of those, the properties of the magnetic material will realign themselves and actually turn back into another bar magnet with a north and a south end. Okay. And so here's another. So magnetic dipole, when placed in a magnetic field, will align to that magnetic field. Materials composition influences the behavior and the presence of any external magnetic field. And one thing that you can also see over here is the Earth. We can treat the Earth as a bar magnet, and you can see here. So you'll see that the geographic north and south poles are at an angle to the magnetic north and south poles, right? And so if you just remember, again, everything will go, right? We'll go point from north to south, okay? And then finally, materials. So magnetic permeability, that's very much like the electric permittivity. So the magnetic permeability is a measurement of the amount of magnetization in a material in response to an electric external magnetic field. And then finally, there is a constant, sometimes referred to as vacuum permeability or magnetic permeability. And mu 0 has a value of 4 pi times 10 to the negative 7th Tesla times meters over area. So the unit for magnetic field strength is Tesla, not named after the car, but named after Nikola Tesla, who did a lot of research with electromagnetism. He's a very interesting character, if you want to say the least. He did Tesla coils. He did, if you see any pictures of a scientist sitting in a chair, reading a book or sipping coffee, with all these electric field or with these lightning bolts passing over the top of him, that's Nikola Tesla. He was just an amazing scientist in this field of magnetism. Okay, so again, like there's not much in terms of calculation here. So you got the B dot dA equals 0. That's Gauss's law of magnetism, which is the second equation of Maxwell's equations. And then the vacuum permeability or magnetic permeability, which is that 4 pi times 10 to the negative 7th. You're going to see that show up in a lot of the equations that we work with from here on out. And in the next video is when we're going to start talking about forces and how they affect moving charges.